So welcome to 4.2 notes. This is going to talk about something called summation notation, which some of you might already be familiar with. We're going to start with a question that may sound pretty tedious. I want you to add up the first 100 positive integers. If you already know of a slick way, or if you think you can find a slick way of doing this, then pause the video and give it a try. But please do not just add them in order, because that's not going to help us in our method. So pause right now if you can do it. Otherwise, just keep on watching, and we're going to see a nice slick way of doing this. So what we want to do is we want to notice that because this is a series of numbers that are equally spaced, we can take a look at this and this, the first and the last, and we're going to add these up, and we're going to see that that's going to add up to 101. And if you try that with the next pair, you're going to find that that also adds to 101. And if you try that with the next pair, you're going to find that that also adds to 101. And of course, since they're evenly spaced, you're going to find that this is going to happen for all values, all pairs. We're going to get lots and lots of different pairs of 101. So I guess the question is, how many 101s are we going to get? And we're just going to multiply 101 times that number of pairs we have. Well, if we have 100 numbers and we're pairing them up, then it should be pretty obvious that we have 50 pairs. So we're going to multiply 101 times 50, and we're going to get 5,050. And that is a really slick way of adding up the first 100 positive integers without going in order: 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, etc. Alright, so I would like for you guys to give this a try. We're going to try to use that same slick way to evaluate these. Oh, there are only two. These two sums. Of course, we could do this by hand very, very slowly if we added up every single one of them. But give it a try, pause the video, and use that same slick way, and see what you can come up with. So if you've already worked this out, then you should see that, again, this and this are going to add up to 8,324. And this are also going to add up to 8,324. And this are also going to add up to 8,324. And in fact, we're going to get a whole bunch of different 8,324s. Now, the question is, how many 8,324s do we have? We can't really count them because there's this ... in the middle here, so because there were too many to list out all of them. So we're going to have to count these somehow. But it should be pretty clear, I guess, that that this pattern is that this is 4 times 1 plus 4 times 2 plus 4 times 3 all the way up to plus 4 times 2080. So, since we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 2080, that means we have 2,080 different numbers in our lists, and that means we have half of that many, or 1,040, in pairs in our list. So that's how many 8,324s we're going to multiply together. And I don't have a calculator handy, so I'm just going to go ahead and leave it like that, but it's pretty easy to pull out a calculator and double check that. So that would be how you would do that one. The next one works pretty much the same way. Let me get back to my default colors here, and we got negative 100 plus 71, and I guess we've got that would add up to negative 29, I think, pretty sure. And then the next pair, negative 97 and 68, well, this one went up by 3, while this one went down by 3, so that sum should be the same thing of negative 29. I hope that's right. Yeah, that looks right. Yeah, I'm pretty certain that I'm doing this correctly. And the negative 94 and the 65, they're also going to add up to negative 29. So we've got a whole bunch of negative 29s that we're adding up. And the question is, how many of these are there? Well, this one's a little bit harder, but if we remember how to create an equation using a series of numbers that are equally spaced, this is an arithmetic series, increasing by 3 each time. We have 3, well actually let's write it off to the side. We've got 3 times some number plus some starting value. Well, if we start with 1 like we did up here on this multiples of 4 problem, I'm going to think, well, 3 times 1 would be our first value, and that's going to give us a 3, obviously, but we want our first term to be negative 100, so what can we add to 3 to get negative 100? That's going to be negative 103, and that should make it so that this first number is going to be 3 times 1 minus 103, and this is going to be 3 times 2 minus 103, because it's 3 bigger than the last one. We've got one more 3, and this is going to be 3 times 3 minus 103, etc., until we get all the way up to 71, which is going to be 3 times some mystery number, again, minus 103. So I'll do a little scratch work over here. 3 times some mystery number minus 103 equals 71. So if we solve for that mystery number, we'll get, give me a second here, some basic algebra here. 3 goes into 17 5 times with a remainder of 2. 3 goes into 24 8 times. So we've got 58. So that tells us that we started off with 1. We got all the way up to 58. That means we have 58 terms here. If we have 58 terms, then how many pairs do we have? We have half of that, which is going to be 29. So we've got 29 times negative 29. And again, I don't have a calculator handy, so I'm just going to leave it like that. But you guys can punch that into the calculator or multiply it out by hand if you have the inclination. Alrighty, so that's a nice slick way to add up numbers if they fall into an arithmetic progression. Again, that means that the numbers are increasing by the same amount each time. In other words, we can have a linear equation represent the values. Alright, so now we're going to talk about these same sums. These problems can be written in something called summation notation in a much more compact way. Instead of listing out all 100 numbers, or using the ellipses that I've got right here, whoops, sorry about that, the ellipses that I've got right here, we can use something called summation notation. This sigma here is a Greek letter. It stands for sum. S is the first letter in sigma, and it's the first letter in sum. And what this tells us to do is to add up all the different values of I, starting with I equals 1 and going to 100. Okay? We saw on this problem right here that we weren't adding up I each time. That would be 1 plus 2 plus 3. But we were adding 4 times 1 plus 4 times 2 plus 4 times 3, all the way up to 4 times, I guess it was 2080 was what we had. So that told us that we started with I equals 1, and we went up to I equals 2080, but we weren't adding I each time. We were adding 4 times I. So I'm going to put a 4I right here, and that's a nice compact way of writing that summation. Same deal with this next one. We saw that we were going up by 3 each time, so we had 3 times 1, and then we said that was minus 103, and then 3 times 2 minus 103, and then 3 times 3 minus 103, etc. So we had 3 times I minus 103, and I think we had 29 terms. Is that correct? I'm going to scroll up because I don't quite remember. We actually had 58 terms, right? Half of that was 29. So 58 terms, so we're going to go all the way up to 58 here. All right, so I starts at 1 and goes up to 58. And that's going to be the instructions for what we do with I. That's going to give us each one of our terms, our first term, our second term, our third term, our generic ith term, all the way up to our 58th term. And once we find all 58 terms, we take the sigma, or the sum of all of those terms, and we add them up, we sum them, and we get a final answer. So again, this is asking the same question, it's just finding a more compact way of writing that same summation problem. Alright,